Previously, we talked about Ohm's law, V equals IR. Um, and how we related that essentially to conductors or even devices. I think we did an example of like a skillet or a frying pan that was acting as a resistor, calculated the voltage or the current across it. Um, so now instead of just talking about individual components, we're actually going to talk about putting these individual things into circuits. With electricity, you can have a current that's either DC or AC. DC means direct current, which is just the flow of charges in one direction. Something like a battery is going to produce DC current um, because it always has the same terminals. So you can imagine just like a regular old battery. One side's always going to be the positive side, and one side's always going to be the negative. So that's going to set up what direction your current's going to flow. In this case, what's going to happen is electrons are going to move away from the propelling negative terminal, and they're going to move toward the attracting positive terminal. On the other hand, AC means alternating current, and that refers to electrons in the circuit that sort of they actually go back and forth. So you can imagine if you stuck a battery into a simple circuit and let it run for a fraction of a second, then flip it and put the battery back in, then flip it. So you can essentially keep going back and forth, flipping this battery over and over and over. And that's essentially what an alternating current is. So instead of electrons moving in like one direction over time, they actually sort of jiggle back and forth. If you were to plot the current over time, so as time progressed in a DC circuit, you see that the current is constant, it never changes. And then current in an AC circuit actually alternates. So it'll go positive to negative to positive to negative. Remember, your current is your flow of electrons. So you can see that you sort of get electrons that jiggle back and forth. Generally, most of the world, especially here in the US, residential and commercial circuits are AC, because with AC, you can actually step AC up to high voltage, transmit it a long way, and actually not lose a lot of heat. You can imagine with electrons bumping into each other in some sort of conductor, you lose a lot of heat that way. Or you lose a lot of energy to heat because you have all these collisions. Ideally, you would just want the electrons to flow directly, but that doesn't always happen because there's some jostling around. So that's why here in the US, because the US is a very big country, we transmit our energy by stepping it up to high voltage and then transmitting it that way because we don't lose a lot of heat. It's more efficient. Um, so once this energy gets to where it's going, we can actually step the voltage back down. So we transmit it with giant voltage across power lines. We can step things back down once it gets to the home or the business, whatever is going to be using that energy. Typically, the voltage in North America is AC, and it's normally 120 volts. And that's just because in the early days of electricity, higher voltages burned out filaments. So basically, light bulbs, the filaments inside, they wouldn't last very long at high voltages. So when electricity was first introduced publicly and commercially, they had to use lower voltages, so 120 volts. By the time electricity became more popular in Europe, so like overseas. By then, engineers had figured out how to make better light bulbs that didn't burn out as easily. So Europe actually was able to, when they implemented electricity, publicly and commercially, they actually could step up their voltage. They doubled the voltage to 220 volts. Interesting fact, in Europe, they actually use DC voltage and not AC, at least in some parts in Europe. That's because everything is much more compact and closer together. European countries are much smaller than the US, so they don't have to transmit as far. Even though that household current is AC, a lot of battery operated devices, like your laptops, smartphones, things like that, a lot of those are actually DC. So you can essentially convert from it like a wall outlet plug AC down to DC, and when you plug, that's exactly what you do when you plug in your laptop or your phone to charge it. Over here on the right, you see a few different types of transformers that do this. You see a large one that steps down industrial size voltages to something smaller. So here are the typical transformer that you can see on power lines outside your house. This goes from the high voltage, from the power lines down to the 120 volt DC, or sorry, the 120 volt AC that your house uses. And then I was hoping I could find one, but I don't have one handy. The charger, like here, that you could use for your phone. That's actually a transformer because it takes that 120 volt AC from the wall and steps it down to about 12 or 15 volts is usually what your phone would use to charge. That might actually be a little high for a phone. I think laptops are like 12, 18, 24 volts, something like that. So this is essentially done, but at least what's inside the transformer is a diode. Here's some pictures of diodes. A lot of these are like the little lights you see like on a TV remote. If you press it and a little light lights up, that's actually a diode. So a diode will actually let current flow in one way. Okay, so I'm going to say the diode restricts current flow to, oops, one direction. Right? And then to smooth out the signal, they actually use a capacitor. Remember that a capacitor is just a fast battery. We talked about those last time. So this is just a fast battery. You can charge them really fast, and you can also discharge them really fast. It's not instant. It's just quickly. So everything we just talked about, we can sum up in a nice graph. So you can imagine if your voltage or your current, whatever's plotted here, doesn't matter. So the output voltage could be huge, but when it comes in, it steps down, right? So if it's coming in from the power lines, it'll be stepped down to like your 120 volts AC. We can see it's alternating because it's going positive to negative. Now, in part A here, this is just stepped down, right? So it's going to scale down this oscillation to what we want it to be, whatever we're charging, or whatever device is plugged in, that gets taken care of. Next, the diode. The diode is going to chop off the current in one direction that we don't want. Remember, a diode will only let current flow in one direction. So it looks like it's going to stop the negative direction flow. So these simply go away. So on the other side of the diode, all we're seeing is just the positive swoops, so to speak. From there, in picture C, we're going to stick in a capacitor. And because a capacitor is not instantaneous, it takes just a little time to charge and discharge. What you're seeing here is essentially it's trying to charge. You can see it increasing, but it doesn't get all the way up there, right? it doesn't hit the peak anymore because the input switches to negative or starts decreasing before the capacitor has time to fully charge. So as this goes up, before it can like reach its maximum peak, it's going to start going down again. Okay, so here's the charging of the capacitor. Here's the discharging. And this is just going to happen over and over and over. So you can see what we're looking at is we're starting to get more of a straight signal. That's the red line here. So this red line is starting to look more like DC. We'll say it's almost like a DC current. Now this final piece is just a situation where you can actually use two diodes, and we won't get into the details of how this works, but essentially you can use two diodes and sort of recover the missing piece. So what was over here that was cut out is now inserted again. And that's going to keep your your capacitor from discharging so much. So instead of having these deeper valleys, it gets hit again by another pulse, and you can get even closer to that approximate DC voltage. So when you tune all these components, if you're very careful, you can essentially create a nice flat DC signal. All right, let's talk about what's actually going on inside these wires and these circuits. So current is established through the wires at nearly the speed of light. That means as soon as you like connect two terminals, like over here in this picture, let's use a different color. As soon as you connect these two terminals, you have an instant current. But the speed of the electrons moving from the negative to the positive, they don't move that fast. It's just the current is set up that fast, okay? Electrons in a metal or any sort of conductor at room temperature, they do move with really high speeds. They're zipping around in there. They're not going far because they're being jostled, but they're doing it quickly. But because their motion is random, there's no like net motion. There's no net velocity. They're just kind of in there bouncing around doing their own thing. But when a battery or generator is connected to this metal, when you connect those terminals, you instantly establish an electric field inside the conductor. So they continue their random motions, right? They're still bouncing around, but they're sort of nudged in one direction. They're sort of slowly nudged toward the positive. This is what sort of drives your current. So even though they're moving quickly, their movement is sort of just very slow. You could think about it kind of like leaving a concert, like a big concert. So if you're leaving your Taylor Swift concert and everyone's moving to the exits, like you could be bouncing off of people, trying to nudge your way through. You might have a quick velocity yourself, but the crowd as a whole is moving very slowly. And that's the idea here. So essentially, just like the hallway example that we talked about with resistance, the conducting wire acts like a guide or a pipe for the electric field lines. So when you actually connect terminals, in this case, like on your battery here, the conducting wire, the metal wire, actually that sort of acts like your guide for those electrons. Notice that it actually changes the electric field lines. So previously you see that the electric field lines, before anything was connected, oops, I drew those backwards. They should be pointing toward the positive. There we go. So you see that these are going from the negative. I'm an idiot. I had them right the first time. My apologies. Let me try this again. We're going this way. from the positive to the negative, because that's what we do. We go out from the positive to the negative. I don't know if I'll be able to erase this and make it better. Ooh, I can. Sweet. Okay. Let's try this again. So the electric field lines radiate from the positive to the negative. There we go. Much better. Now, you see that just like last time, it's just going in that typical arc from 2-point charges. But as soon as you connect this cable, notice you start getting some really weird things going on in your electric field. We won't talk about that in this class, but if you're interested, I suggest you take the physics 1 and 2 sequence. It goes into a little more depth, a little more math, and you can explore these ideas in much more detail. All right. If the voltage source is DC, the electric field lines are maintained in one direction, right? We see that here. This is DC. Electric field lines are maintained in one direction. And then, of course, the conduction electrons are accelerated by the field parallel to the field lines. So that means these things, you're just moving in the same direction as the electric field, the electrons are. The jostling of these electrons is actually what produces heat. So just like we said earlier, when these electrons move, they're bouncing around between all the other things inside the conductor, the impurities, the other atoms. And if you ever like vacuum and then pick up the cord to the vacuum cleaner and it feels warm, that's what you're feeling, is you're literally feeling the effects of all these electrons just jostling around in there, bouncing off other atoms and such. And again, just because they're moving like crazy in there doesn't mean they're moving quickly toward the positive terminal. They're actually moving very slow. And that very slow group speed, so to speak, is actually called the drift velocity. That means, of course, in AC current, the one that alternates, the conduction electrons, they don't drift. They're just sort of chilling there and they bounce back and forth. So there is no drift velocity in alternating current circuit. Do keep in mind that the electrons, that are the conduction electrons inside of a cable or a wire, they don't get accelerated because they bump into each other, right? Not because they bump into each other. They get accelerated by the electric field. So you have to have that electric field for things to be accelerated, or for electrons to be accelerated. This is true for all the electrons in the entire closed path of a circuit. They all react simultaneously. So as soon as you set up that E field between your positive and negative terminals, like on the battery, you don't like start a domino effect. You literally just, they all start moving at once. So it is certainly not bumping into each other. It is all of them go at the same time. It's sort of like if you're in marching band, you don't wait to be nudged by the person behind you to start moving. You all know what you need to do and you do it all at the same time. Those electrons also do not come out, like if you plug in something, those electrons do not come out of the wall and flow through the circuit. The source of the electrons in the circuit are within the material itself. They were already there, okay? So when you plug something in, when you plug in your cord, you're using the electrons in the cord to your vacuum cleaner or your toaster. You're not getting electrons out of the wall. Think here, yeah. Just an example, if you plug in a lamp, that's what happens. So a charge moving through a circuit expends energy So either that circuit is going to heat up, or you're going to use that energy to like turn a pump or something mechanical. Either way, you've got to deal with that energy that's being released, and usually it's done by heat. We can actually calculate the rate at which electric energy is converted into other energy, whether it's heat or mechanical or light even. And this is actually called electric power. You all have probably seen that. It's the watts. It's represented by a W. So electric power is equal to the product of the current times the voltage. Okay, so power is watts. We know currents in amps, the voltage volts. So to shorten this, we already know what the current and voltage are. It's I and V, and then power is just capital P. So P equals IV. This is very similar to Ohm's law. And for the math folks out there, if you wanted to, since V equals IR, and there's a V here, we could, if we wanted to, we could say I. Now we're going to replace this V, right? It's V. It also equals IR. So we could totally replace it because this is, after all, this is V. V equals IR. Notice we have I times R now. So this really is just I squared R. So this is just another way to calculate power if you need it, I squared. So the current squared times resistance. If current is expressed in amps and voltage in volts, that's usually true. Then the power is expressed in watts. Okay, so here's just a reiteration of those units: watts, amps, and volts. For example, if a typical incandescent light bulb is rated at 100 watts, usually are, this means that when operating on 120 volts, it draws a current of 0.8 amps. And you can plug these in, check the equation, and you get roughly, it's not quite 100, but as an approximation, you get about 100 watts. This will let you actually calculate if a circuit is safe to touch or not. Because if you knew you plug a lamp into a 120 volt wall outlet and you know you got a 100-watt bulb, you can calculate, just do some algebra and calculate the current through it. We see that 0.8 amps is actually pretty big and can be dangerous. We talked about that last time. Something else we can do instead of just calculating wattage is, since that power is energy per time, just like from way back when we talked about work and energy, power is work over time. Well, that really is just energy over time, or a change in energy over time. So we can actually play a game here where we multiply the T over, right? This is T, this is power, this is energy. We can do some algebra and essentially just multiply the T over, and we get power times time equals energy. This right here, power times time, is how the electric company sells you your energy. Because normally power is in watts and time is in seconds. So we could call this, let's see, energy. Man, I cannot write. There we go. We could call this energy. You could say the units are in watt seconds. I mean, that's fine. That's totally true. It's a little wonky, but it's no big deal. But how the electric company is going to sell you your energy, right? Just bulk how much you use is going to be in a kilowatt hour. Kilowatt hour. So if you ever look at your electric bill, that's usually what's going to be on it, is a kilowatt hour. Let's look at this example and then we'll stop there. So if an electric company charges 15 cents per kilowatt hour, that's 15 cents per 1 kilowatt hour, what would it cost to operate a 1.2 kilowatt hair dryer for 1 hour? Okay. So let's think about this. We have a rate at which we have to buy this power. So this is our rate. Now, what is the power requirement of this hair dryer? We know that that is 1.2 kilowatts. And then we want to run it for 1 hour. Okay. Now we can use this definition of energy equals power times time. Okay. So here is our definition of energy. A kilowatt hour is a unit of energy, power times time. So this is power times time. Now we just need to multiply the rate at which we have to buy that energy. Okay. So this is just delta E. We multiply by the rate that we are buying that energy, 15 cents per kilowatt hour, and we get, takes about 18 cents to run a hairdryer for an hour. I'm checking. Yeah, that sounds right. Okay. So, yeah, all we need to do is just think about this in terms of the amount of energy we need. And then the rate is just how much that costs over the unit energy that we're looking at. So with that, I will stop. The next thing we'll talk about are just the different types of circuits. We're going to talk about, focus right here, have a look. So we're going to talk about series circuits and parallel circuits, and then some circuit safety like fuses and overloading. So until then, if you have any questions, please let me know.